Today we will guys please. Today we will talk about TinyOS. We will start looking at how to implement simple applications using this operating system for wireless sensor networks. Okay, we'll look at how the operating system works, and we will basically implement two very simple applications. I've also here with me some very little sensor devices. So I will show you how to basically deploy one application on such real hardware, and we will also do basically simulate the application that we will write on the graphical simulator that we have available on the virtual machine. Okay, so basically what we will do today is start looking at the operating system, start understanding how it works, developing two very simple applications, looking at them onto the real hardware, and looking at them in the simulation. Okay, since you will basically work mainly on simulated code, then it's good for you to learn how the simulation works starting from now. First of all, any question regarding the previous lectures? Everybody managed to run the virtual machine? Everybody managed to, if you tried to have an account on TeamSpeak, did you try to plot some data? Any particular comment on that? Nobody? Okay. I've also started putting together some projects. Okay, so expect them to be let's say expect the description of them to be online in 15 days. Okay, so that you can start looking at what I mean with these projects and start understanding if you may want to do one or you may want to propose something from your own. Okay, so I think we can start. You can also start booting up your virtual machine, since we will use it today. So it's good if you have it open in front of you. Okay, cool. So as I was saying, today we will play with TinyOS, and we will look a little bit at how it works, the main building blocks. We have seen already something like this in the very first lectures. So we will see again the concepts of components and interfaces and how to glue together these two different components using interfaces basically. Then we will see a very simple application called the Blink application, which is basically an application that just turns on and off LEDs, so basically lights on a sensor node. Okay, so we'll see basically this hardware blinking with different colors, and then we will start using the radio. Okay, so we will start using radio communication, and that's why I have two of this sensor. We will also play a little bit with message exchanging between two nodes. Okay, and that basically gives you a very important primitive to then start implementing applications that are based on wireless communication. Okay, and we will not look at the TinyOS simulator today. We will look at another simulator, which is the Kuja simulator, which is a little bit more interesting because it's let's say graph-based. So you have actually a nice graphical interface where you can put nodes inside and move them around. And I will leave the TOSSIM simulator for the next lecture when we close our discussion on TinyOS, basically. Okay, so let's start looking a little bit at the details of TinyOS. Again, don't be worried if what I'm going to say now may seem a little bit obscure to you, okay? Because when then we move to the example, we actually look at the code in your virtual machine, then everything should be hopefully more clear to you, okay? So, first of all, what is TinyOS? We have already said that TinyOS is, first of all, an operating system for wireless sensor network. We have made a discussion on why we need an operating system which is different from the traditional operating system that we use on standard PCs and laptop architectures. Do you remember why we need such a different and new architecture for an operating system when we talk about wireless sensor network and in general about the world of Internet of Things? What are the differences that we would like to have? Anyone? So we have talking about constrained resources, okay, on this hardware. So what is the differences that are inside this hardware with respect to this one? Okay, we have talked about reduced memory, for example. Okay, we are talking about gigabytes here, kilobytes here. We talked about processing capabilities, okay, in terms of processor speed. We're talking again about gigahertz here, megahertz here, okay? And then we talked about, and most importantly, energy consumption, okay? So this one here can be powered with a main source or with a lithium battery, which make it last for 10 hours maybe. On such a hardware, I have two AA batteries, okay? So that's the main difference. So also the software that is running here should be adapted to these differences, okay? And we want the operating system to be very light, okay? Very small in comparison to what we have on standard architectures. So that's, let's say, the main motivation on why we would like to have a different operating system. So there are many operating systems that respect such, let's say, features. TinyOS, as I said, is one of the most famous one, and in particular, it's not only an operating system, but it's basically a general framework that gives you all the tools that you need in order to develop applications for wireless sensor network. Okay. If you want, let's say, a nice introduction and some guidelines on TinyOS, there's this nice document here, TinyOS programming, that you may want to read, not into the details, okay, just have a look at it. And it basically gives you a nice introduction on the world of TinyOS, okay. Now, the first thing that you have to understand about TinyOS is that it is basically C programming language, okay? So I don't know if you have already seen C programming language in one of your previous courses. How many of you have seen C? I guess many of you, good. That's good. So you will not see a lot of differences in the syntax, okay? Meaning how we define variables, how we define for loops or conditional statements. The differences will be more in how you use this syntax in order to write application, okay? So there's no concept of main function. There's no, it's a little bit different, but in terms of syntax, it's basically C. If you want actually the correct definition, TinyOS is written in NES C, which is a dialect of C. So we have the proper C syntax plus some structures which are properly defined for TinyOS, but nothing very difficult to understand. So this NestC and in general this environment of TinyOS provides everything you need to develop application. In particular, we have, let's say, syntax for defining and using commands, events, and tasks. We will look a little bit again at this. Define variables, allocate memory in a static way. Okay. Remember that we do not have function pointers. We have just proper functions and these tasks which are a little bit different from functions. We will learn how to use them. And when we talk about an application which may be, let's say, compared to a C program, when we talk about application, then we are basically talking about additional components which we write and which we basically add to the operating system. And these components are created by starting by basic components. Okay? So basic components may be the module for starting the application, the radio communication, the module for using the lights, and so on and so forth. And when we develop an application, basically we take what we already have from the operating system and we wire it in a proper way according to what we want to do. So it's in, let's say, we have 4 main different types of blocks when we write a TinyOS application. And it's important to understand why do we need them and what are the differences in them, okay? So the traditional TinyOS dialect, let's say, identifies these 4 different, let's say, blocks: modules, configuration, headers, and interfaces, okay? So we have these 4 keywords, which basically then reflects on 4 different source files that we have to write in order to start with an application. So we have modules which provide the actual code implementation, okay? And so modules contain the actual logic of your application. And they contain, so basically, the set of instructions that your application has to perform in order to do what you want it to do. Then we have configurations, which are the files where this gluing and wiring between different components is specified. Okay? Again, if it can sound a little bit obscure, it will be clearer in a while when we look at the source code. We may have then headers, which are just files which contain, for example, the value of constant variables or the structure of the message or the packets that we want to transmit on the wireless channel. So as in C, in standard C, header files contain, let's say, utility values or constant values for being used in your application. And then we have interfaces, which are basically a user guide on how to use modules. Okay, so interfaces do not contain code. Okay, they just contain the set of commands and events that you can use on a particular component. So they are basically instruction manuals on how to use components. And you can either use the interfaces which are already contained in the TinyOS operating system, or you can create new interfaces when you create new components. Okay? So you can write your own instruction manuals on how to use some components. So you can start creating little components and then building on top of these little components, enlarging your application. Just to give you an example with some code. Here you see two different interfaces. What? Sorry? I don't understand. Ah, okay. Okay, now it should be okay. So let's look at these two examples. So when we talk about interfaces, and you should not, let's say, make this mistake and, let's say, take interfaces for components or mix them together. So interfaces do not contain any code. They just contain these definitions. For example, the interface standard control, which we use basically in any application, and it's the interface that it's used to start and stop components, just contains these three commands: init, start, and stop. That means that if you decide to use this interface on a component, then you can initialize, start, and stop the component, and that's it. Okay. Another interface which is commonly used in application is the timer interface. And the timer interface basically is the instruction manual on how to use timers. Okay? And if we read it, we see that when we use a timer, we can start the timer, stop the timer, and these are two commands that we can call on the timer components. And occasionally, the timer component can trigger or can fire an event, which is the event fired. So when the timer expires, we expect an event to be triggered from the timer component. Okay? So interfaces are instruction guide on how to use components, and they basically explain to the developer what kind of commands can be called on a particular component, so what kind of actions can be made on a particular component, and what kind of events that particular component may occasionally trigger. Okay, so asynchronous events that or interrupts that the component may trigger. And we will learn what are basic interfaces. For example, the timer interface is a very, very basic interface that it's already inside the TinyOS operating system, and most applications out there use at least one of these timer interfaces. Any questions so far? I know it may sound a little bit strange without looking at the application itself, but we will look at one in a while. Okay. Now, so we have seen what is the difference between configuration and modules. We have seen interfaces, okay, instruction guide for components. Now, a component is basically defined by configuration and modules. So two different keywords. And again, the difference is that modules are used to implement the commands and events that are defined by interfaces. Okay, so the actual code that you want the application to run when you call init, start, or stop on a particular component is contained in the module. Okay, and when you build complex applications, you can put together different modules, and how you put them together is specified in the configuration file. Okay? We will see examples about this. So just remember that interfaces do not contain code and are just the instruction manuals on how to use components. Modules are the implementation of the commands and events contained in interfaces, and configurations are the logical wiring that you decide to perform in order to build a complete application starting from simple components. Okay, that would be a good explanation on what are the differences between these three keywords. Always remember that you can have additional header files where you may want to specify constants of your application. For example, the sampling period of a particular timer, the length of the payload of a particular message, the frequency channel that you want to use in order to exchange messages within your application, the maximum number of nodes that are supported in a particular application, and so on and so forth. Okay, but that's just let's say a detail, I would say. So let's look at a very simple application in order to understand how the things I've said so far relates to an actual implementation. And as I said at the beginning, we will use this Blink application, which is the most stupid application you can think of. And what it does basically, it keeps 3 timers at different frequencies. One timer at 1 Hz, one timer at 2 Hz, and one timer at 4 Hz. That means one timer expires every second, one timer expires every 500 milliseconds, and one timer expires every 250 milliseconds. Okay, so 3 timers which expires at different periodicities, and each timer is connected to a particular LED, to a particular color of a light. Okay, whenever a timer expires, the LED is triggered on or off. That means that particular light is turned on or turned off. Okay, so if you want to understand better what it looks like, I don't know if you can see the 3 lights blinking on this hardware, but it's exactly what I have explained. So I have 3 LEDs, the blue one, the red one, and the green one. And as you can see, the blue one is triggered on and off every second, so every 1 Hertz. The red one is the fastest one, every 250 milliseconds, and the green one every 500 milliseconds. Okay, and this is exactly the Blink application that we will see now ported on this particular hardware. Okay, so we will see how we can do this. In order to do this, we will use just 2 files, a configuration file and a module file. So you have the code here, but you can also look it directly in the virtual machine, and that's what we are going to do now. Okay, so move to the virtual machine. Okay. So all code of TinyOS is contained in the folder, let me see, TinyOS main here in the root directory. So if we go here, TinyOS main, can you see, or maybe I have to turn off these lights. Okay, better. So if you go inside this folder, you have a subfolder called apps, which contain all the application in TinyOS. So you can go inside. And so there are already some example application. In particular, we will look at the Blink application here. Okay. So you can either use the terminal or use the, let's say, the graphic interface to go there, which would be basically here, home, TinyOS main here, apps, blink, and we have a bunch of files inside here. Let me just do like this. So you should see at least these two files, blink.appc.nc and blinkc.nc. So one is the module and the other one is the configuration. So let's open them. You can use the gedit editor. We just need to look at the source file. Okay. And let's start looking at the module, okay, which is blinkc.nc. So this is the module. As I have just said, the module contains the actual implementation of your application. Okay, so the actual code that your application is running. So let's see a little bit how it looks like. So we have an include here. Well, that's just for including the, let's say, functions that we need for running timers. And then we have two main blocks, okay? We have this main block here, which basically specifies what are the interfaces that our module is going to be using, okay? And then we have the implementation part, this part here, that basically fills in all the code which is requested by the interfaces that we are going to use. Let's see a little bit into the details. So our applications basically, as I've said, uses 3 timers at different frequencies. Then it has to turn on and off these LEDs, okay? And of course, since it is an application, we would like to start it and stop it and so on and so forth. So it also uses this boot interface, which is the, let's say, starting point of every TinyOS application. So every TinyOS application basically uses these boot interfaces. So in total, we are using 5 different interfaces, 3 for the timers, 1 for using the LEDs, and 1 for starting the application. Now, the entry point of each TinyOS application is the event boot.boot, which is an event which is triggered by the boot interface when the application is ready to start. So when the operating system have loaded all the proper functionalities and you can start the application. So this is, let's say, comparable to the main function in a C program, okay? For those of you who have seen C, you know that the main function is the first function which is executed when you launch a C program. For the one of you that never saw any programming language, just assume that there's an initial point in each program, and this initial point is the first instruction that is executed by the processor, okay? And in this particular case, the first instruction that will be executed is the first line of the boot.boot event, okay? Which is triggered automatically by the operating system. So what we want to do when the application starts is to start the 3 timers, basically, okay? So as a first step, we say, okay, let's start the timer, and then let's wait these timers to trigger an event when they are ready, okay? So we start the 3 timers, and the 3 timers are defined here as 3 different names, okay, timer 0, timer 1, and timer 2. And we are basically specifying that the time granularity that we want to use in specifying the timer periodicity is in milliseconds, Okay, this tmilli is a keyword of TinyOS to specify that the timer should be configured using milliseconds. Okay, now don't worry about this syntax. Everything is explained in the documentation if you really want. For what we need to do, it is enough to always use this particular syntax for creating timers. Okay, you are not requested to know exactly how timers are working, but that basically explains why when we start a timer we use the function start periodic, which basically start a timer and makes it fire with a periodic behavior every x milliseconds, where x is the value that you pass inside this function. Okay, so timer 0 will fire every 250 milliseconds. That will be the 4 Hertz timer. Timer 1 will will fire every 500 milliseconds. That will be the 2 Hertz timer. And timer 2 will fire every 1000 milliseconds, so every 1 second, and this would be the 1 Hertz timer. Now, you may ask yourself, how can I know that I can call this command on a particular interface? Well, the answer is basically here. If you open the browser and you go to, for example, this address here, well, this is basically pointed on the TinyOS websites on the documentation section of TinyOS. You have basically for each platform that you want to program your application for a set of interfaces and components and all the commands that you can call on these interfaces and components. So for example, if we want to look at timers, we go here in the interface timer, and you have all the commands that you can call on a timer interface. Okay, so for example, the command that I'm calling in the application is the start periodic command, which set a periodic timer to repeat every dt time units. Okay, where dt is the time unit that you pass inside this module. But you can also use, for example, the command start one shot at, which set a single short timer to time t0 plus dt, meaning we do not want the timer to fire periodically, we just want the timer to fire somewhere in the future, and we want to specify when. We have a command to check if the timer is running or not, which returns a Boolean variable, true or false. So we can call it to see whether the timer is running or not. We can call the stop to cancel a timer, and so on and so forth. So, as I was saying, interfaces are the instruction manuals on components, and on the online documentation of TinyOS you have all the interfaces that you can use, and for each interface you have the actual explanation of each component, of each command. You also have the explanation of the events which are triggered by each component, and in this particular case the timer interface has one event which is called the fired event here, okay, which is signaled, so it's triggered when the timer expires, so either one shot or when it repeats, so if it's a periodic timer. Okay, so each time the timer fires, this event will be fired. And what does it mean? It means that the code inside this event will be executed. Okay, So whenever you have events, events will be filled with code, and this code will be executed each time the event is fired or signaled. So when the timer, for example, when timer 0 expires every 250 milliseconds, the corresponding event on timer 0, which is timer 0 dot fired, this event here, will be executed. So what we want to do? Well, what we want to do is to trigger on and off a light each time a timer is fired. So in the code that is contained in the timer event, we will actually write the instruction which is needed to trigger on and off a LED. In this case, so let's assume that I'm completely ignorant and I just know that I want to use the LEDs interface. I go here on my documentation and go on the LEDs interface here, and I get the instruction manual on how to use the LED interface. And I know, for example, that the commands that I can call on the LED interface are, for example, LED 0 off, LED 0 on, or LED 0 toggle. And in particular, I will use this LED 0 toggle, so if the LED was off, I'm turning it on, and vice versa. So if it was on, I'm turning it off. Okay. I have this for the 3 LEDs that are present on this particular hardware. Okay. So this has 3 LEDs, and that's why here I have 3 LEDs interfaces. So what I'm gonna do is, whenever each of these timer fires, I will toggle the corresponding LEDs. Okay, so when timer 0 fires, I will toggle LED 0 here. When timer 1 fires, I will toggle LED 1. And when timer 2 fires, I will toggle LED 2. Okay. Don't look at this instruction here. We will look at them in the second lectures next week. Okay. Just for let's say giving you a hint, these are debug instructions for debugging the correct behavior of your code. Okay. Just assume that they are not present now. Okay. So this is a very simple implementation of a component. Okay. Sorry, a module. So we have 3 timers. Each time one of these timer fires, we will toggle the corresponding LED on the hardware. Okay. It seems quite straightforward. Any question? Yes. Because Raspberry Pi is not cannot be used with TinyOS. Raspberry Pi runs Linux. It's basically a standard PC. Okay. So this is meant for hardware which is even more constrained than a Raspberry Pi. Okay. A Raspberry Pi, it's basically it can be compared with a PC. Okay. It has dual core architecture, 512 megabytes of RAM. You can run Linux on it. Very, very simple. So this is the implementation of the module. Let's look at the configuration file, which is the file in which you specify how interfaces should be connected to components, basically. And this is specified in the blink appc.nc file, which is the other file which is containing this folder. And again, we have this configuration, and in the simplest form, this configuration just contains an implementation section. Okay, and in this implementation section, we will declare what are the components that we will use and how the interfaces which we are using in the module are related to these basic components. Okay. So if we look at the module, we are using 3 interfaces for 3 different timers, the LEDs interface and the boot interface. And in the configuration we need, okay, we must, for each interface we are using here, connect a component which is given by the operating system. Okay. If we do not connect all the interfaces which we are using here with one component, then we will have an error when we compile the application. So you have 2 different parts here. The first one declare what components we are going to use, and the second part actually connects the interfaces of our application with the components we are going to use. And again, the components we are going to use are always more or less the same and are the ones which are already given us by the operating system. So for example, in order to boot the application, to init the application, we will always use the main C component, which provides the boot interface. For using LEDs, we will always use the LED C component. For using timers, we will always use this timer milli C component. Okay? In this case, we have 3 different timer components. So the first part declare the components that you are using, and note that there's a component here, the blink C component, which is actually your application. So your application becomes a component of this list. Finally, what you have to do is to connect the interfaces that you were using in your application, so here, these ones, to the components. So for example, blink C will be connected to main C.boot interface. We can also write here something like this, okay? So the boot interface of our application will be connected to the boot interface of the main C component, which contains basically the implementation of all these start and stop methods. My 3 timers, timer 0, timer 1, and timer 2, will be connected to these components, timer 0, timer 1, and timer 2. And my LEDs interface will be connected to the LEDs component. So by doing this, we are basically adding to our application the functionalities that we need to use the LEDs, to use the timers, and so on and so forth. What is happening at the lower layer is basically that these components, which are already provided by the operating system, contains all the code needed to interface with the actual hardware here. Okay, so for example, the LED C component contains the code for accessing the LEDs and turning them on and off. The timer component contains the code that implements a timer on the CPU here. Okay? We do not want to actually look at this code, we just want to use it as it is. That's why we take them for granted and we connect them in this way. Okay? If, let's say, in a couple of let's assume that there's a developer that provides a new implementation of the LED C component, for example, which is optimized for certain uses or which is basically optimized for energy efficiency. What we just need to do, if we want to use this new component, is to replace these components here with the new provided component, and nothing will change in our application, okay? So we will just use the new provided component as it is. So you can think about these components as some sort of libraries that you can use in your application, and these libraries are provided by someone else. Okay. Okay. So any question on this? Still seems a little bit obscure, right? Yeah, I understand. It was obscure also to me at the beginning. Then when I started playing with it a little bit, it became more easy to understand. That's why a good thing to do is to try to play a little bit with this as soon as possible. Okay. You already have a lot of examples, so you just can run them. So let's see how to run in a simulation this program. Okay. So first of all, we have to compile the application. What does it mean? It means that once we have written the source code, we have to compile it in order to first spot if there are any errors in our code, and second, to produce an executable file which can be loaded on a hardware or which can be used for simulation. Okay. So in order to compile the application, you can use the word make, and then you have to specify for which target platform you want to compile your application. So for example, this particular hardware here is the Telos B platform. Okay, so if I would like to port this application on this hardware, I have to write make Telos B. Okay, so you can try to run it, make Telos B, and you will see some text compiling this Blink application for a Telos B binary that is an executable for this particular hardware. And well, you have some text here that we can, let's say, neglect so far. But the important things that have to be noted here are basically this one, which says that we have an application now compiled in this file here, main.x. So there were no errors basically. And you have also the memory footprint of this application. So how much memory is required to run this application. Now, why this is very important? Because since memory is constrained here, okay, we have, for example, this one has 4 kilobytes of memory, 4,000 bytes of memory. We do not want our application to exceed this limit, okay? We do not want to use more memory than the one which is available on the hardware. That's why it's always very important to check this number here, the number of bytes which are used by application in RAM, okay? We do not want it to exceed our memory on the particular hardware, okay? Otherwise, we can have unexpected behavior at runtime, okay? So if we allocate more memory than the one that we can actually handle, then that's gonna be a problem. So these two information here basically says what is the size of the code of your application and what is the size of the memory used by your application. Very, very easy. What happens if I, for example, in my source code here, I, for example, declare a new variable, like an int. Well, let's use this. I'm declaring unsigned integer, so 8-bit of variable. Let's call it number. Well, that's strange. Well, let's see it later. So so we have compiled the application now for TinyOS B, and what we can do, we can port it on this hardware if we have such a hardware. Unfortunately, for example, you don't have this hardware, okay? So how can we run the application anyway, even if we do not have the hardware? Well, this is where simulation comes into play, okay? So since we do not have hardware to run the application, we will use a simulation environment that mimics the fact that we have one of these sensors. And let me just take my slides to see if I have something on this. So why it's good to simulate your application before actually running it? Well, always think about why we need to develop these applications, okay? So we have talked about several application scenarios, for example, monitoring of environmental measures in hostile environments, for example, forests, volcanoes, this kind of stuff. So that means that once you have deployed your application, you will take a lot of these sensor nodes, you will put them around, and then you will start collecting data. So what happens if there's a bug in your application and you spot it just after that you have done all the deployment? Well, you have to go there, take every node, remove the bug, install the new code, and so on and so forth. Okay, this may be very cumbersome to do. Okay, so there's little room in terms of time or money to redeploy the application if you spot an error. So that's very good to simulate extensively your application before deploying it in an actual scenario in order to spot any possible bug that is inside your implementation. Now, this is something that everybody does with software, okay? And it is even more critical when we talk about software for wireless sensor networks, because the let's say process of going and fixing the actual bug may be very, very difficult to implement. You may have to climb a mountain and go inside the mouth of a volcano, for example. So you don't want to do that. So that's why we need simulators, okay, so that we can, let's say, set up a fake or a virtual sensor network. We can try to run the code and see whether it behaves fine or not. And if there are some errors, then we can fix the bug without actually going into the volcano. So we have, for TinyOS, we basically have two simulators. One is called TOSSIM, which stands for TinyOS Simulator, which is the official simulator for TinyOS. And as I said, we will see it next time. Why? Well, because it's a little bit cumbersome to use, and it's textual based, meaning that you don't have a very nice graphical interface of our network. That's why I don't like it very much. But it's very powerful, so it allows you to do a lot of stuff. That's good. Luckily, after a couple of years from when TinyOS was developed, Contiki was developed, the other operating system that we will see. And Contiki has its own simulator, which is a graphical simulator. And very luckily, TinyOS code may be also simulated into the Contiki simulator. So we can actually use this Kuja, which is graphical, for simulating TinyOS application, even if it wasn't, let's say, built for this purpose. So what we will do today is basically we will run this Blink application that we have compiled into the Kuja simulator. Okay, so we will actually see simulated nodes, and we will see that the blinks, the LEDs are blinking basically. So in order to do this, we have to compile the Blink application for TinyOS. We have just done it, okay, with make TinyOS. And then, let's say, follow me on the virtual machine. So you have Kuja on the desktop here. So you can double click on this icon. It's taking a while to me because I have a lot of stuff running there. Okay, so this window should open on your virtual machine, and you can create a new simulation. Okay, so you go here, file, new simulation, and you can enter some parameters of the simulation. We will look at a little bit better at these parameters when we look at Contiki, but let's say you can name your simulation, then define a model for the radio medium. Okay, in this case we will just use the unit disk graph medium, and then you can set some parameters which are, I don't want to explain them now. You can click on create. This will create a bunch of windows. Okay, we have the network window, and as you can imagine here, we will see the actual network composed of our nodes. Then we have the simulation control, start, stop, pause, reload, and so on and so forth. And then we have a window for taking notes if you need to, for example, taking notes on the behavior of your sensor network, the output of the nodes, we will look at this later. And then we have a timeline window here at the bottom where events will be shown, okay? For example, LEDs blinking and this kind of stuff. So what we want to do is to create a new mode, and in particular we would like to create one of these TinyOS nodes inside the simulation, and we will load the code that we have compiled on the simulated node. So we can go here in the menu on modes, the third voice, add modes, create new mode type, and we have several different hardware we can use for our simulation. In particular, we will use the Sky mode. Sky is another name for the TinyOS mode. Okay, so we will create one of these Sky modes. Again, you can add a description for your mode, and then we have to load what is the application that we want to run on our mode. So we will browse here, and we will go inside TinyOS main, apps, blink, build, which contains the executable that we have compiled, TinyOS, and then we have the main.x which is the executable which was compiled by our simulator. You remember? Here, where was it? Here, when I wrote make telos b, the output was that the application was compiled to build telos b main.x, and this is exactly the file which we will give to the simulator in order to be run. Okay. So once you have done this, you can click on create, and the simulator will ask you how many of these nodes you want to add. We will add just one node, but you can add more if you want. You can position them into the space, so you can either select a random positioning in space, or you can actually give coordinates to your modes. So you can put your modes into space where you need them to be, and then you can click here on add modes, and one mode will appear here as a basically little circle with a number on it. Now we can start the simulation and see what happens. Okay, basically what we should see is something like this. So a mode which basically triggers its LEDs with a periodicity. So first of all, you can go here on speed limit and put 100%. It's used in order to match the processor speed with the actual speed of your simulation. Let's say it's a little bit tricky to explain, but if you do not put 100% here on speed limit, then the milliseconds that we have put into the timer are not actual milliseconds, okay? Will be something that depends on the speed of your processors. So this 100% here is to make the time constant in your application actual milliseconds. And then you can, once you have done this, you can click on start, okay, and something will happen. So on the event timeline, we will see the colored bar which corresponds to the LEDs. And if you want to have a more detailed explanation, you can right click on this mode, and for example you can click on show LEDs on sky 1, and this is basically what happens. So you see your application, which is basically performing exactly as this one. Okay, so that's how we can simulate, for example, an application which is blinking LEDs. Okay, now we will look a little bit more into the details of this Kuja simulator, but this gives you a starting point on how to simulate virtual sensor networks. Okay. There was also a nice where was it? Let's see. Wait just a second. No, don't remember where it was. Maybe here. Okay, so you can also show the LEDs directly on the simulation here. If you go on this little menu view, on the network, and then you can basically select what kind of output to see. If you toggle here on LEDs, you should see 3 little LEDs here which are actually blinking with the timers that we have set. Okay, so this gives you a very basic start with TinyOS and how to simulate applications. Any questions so far? Okay, so what we can do is to move to something a little bit more interesting, which is using radio communication. Okay, so how can we, for example, add another sensor node to this simulation, how we can exchange messages between these two sensors. Okay. So again, TinyOS gives you already everything you need to perform radio communication. Okay, so it already gives you the components and the interfaces needed for creating messages, transmitting messages, and receiving messages. Okay, so that's cool because we don't have to spend a lot of time in implementing stuff. Okay, the 8.2.15.4 stack is already implemented in TinyOS, so we don't need to bother about implementing, for example, physical layer stuff, modulation, this kind of boring stuff at the lower layer of the stack. We can just use the upper layers. So basically defining a destination and a source address for our messages and filling the payload of our messages. So the data which is contained in the message that we want to exchange. So the functionality that TinyOS gives to you in order to transmit messages over 8.2.15.4 is the so-called active message extension, okay, or active message layer. So every message contains what is called the active message ID, okay, which is a unique code that can be used by specific applications. Okay, so think about it as a filter that applications use in order to select which messages they can accept and which messages they have to discard, basically. Of course, we need, if we want to transmit and receive messages, we need two components at least. One component that is the one that sends the messages, and how this component is going to work is basically like this. So we will specify the component, we will request it to perform a transmission, we will use a particular command in order to transmit a message, and then we will wait for an event to come back, and this event will basically inform us of the status of the transmission. So it will inform us on the fact that the transmission was correctly performed, or on the fact that some errors were encountered, okay, so that we can take countermeasures. At the same time, we have a receiver module which, as you may imagine, signals an event each time a message is received. Okay, so we will use a sender and a receiver, two different components. So the sender works like this. You first prepare a message, so you put inside the data that you want to transmit. Then you specify the destination, so you fill a particular field specifying what is the destination of your message. It can be broadcast or it can be unicast, okay, so it can be transmitted to all nodes in range or to a particular node in range. Then you call a function to pass the message to the operating system, so to TinyOS, which then will pass this message through all the stack of 8.2.15.4, okay? And then you will wait for a feedback from the operating system, and this feedback will basically be good, we have sent your message, or there was an error. Okay, so 1 or 0 basically. The receiver works like this. The radio stack intercepts a message. It will decode it and perform all the operation up to the basically application layer. And when the message is correctly decoded, then an event will be fired or signaled. And you have basically to write the code inside the reception event in order to, for example, read the message that you have received and perform actions on the basis of the data which is contained in the message. There are a couple of abstractions already included in TinyOS which can be used for message manipulating. So the type of data which is used in TinyOS for sending message is the so-called message T data, which is basically a structure type. So this variable has different fields. In particular, it has 4 fields: header, data, footer, and metadata. Header, footer, and metadata are structures which are transparent to the users, so are basically used for the operating system for operating system purposes, while the user has access only to the data part of these structures. And as you can imagine, in the data part we will fill the data that we want to transmit, basically, very simply. Now, if you wonder what's inside header, footer, and metadata, for example, in the header we have the 8.2.15.4 header, okay, which you should have seen during the lectures with Professor Cesana, right? Have you seen it already? No. Yes or not? Okay, so you know that in the header you have the source address, the destination address, the frame control field, and so on and so forth, okay? All these fields are contained in the header here. In the metadata field you have other fields, such as the transmission power that you want to use for this transmission, the received signal strength, which is estimated by the receiver, the link quality indicator, and this kind, the CFC, the acknowledgements, these kind of fields, okay? So information which are not part of the meaningful part of the message, but still can be used for doing several stuff. In terms of the interfaces and components that are used for message reception, we generally use these 5 here, listed here. So AM, which stands for active message packets, which is used for manipulate packets, so setting fields, setting the source and destination address, and so on and so forth. Then we use the send or AM send message for transmitting packets, so requesting the operating system to transmit a packet for us. And then we have the receive interface for receiving packets. Again, don't be scared about the amount of information that I'm telling you, because at the end of the day you will just use always the same 4 or 5 interfaces for radio communication, okay? And you don't need to learn them to know them exactly. You have the documentation, so you can directly go there and see how to use them. So for example, the AM sender C component provides these interfaces. It means that when we use this component, we can call commands which are provided by these interfaces. And if you wonder what they are, again, let's go on the source code. And for example, if we look at the AM send interface, we have 4 commands, okay? Cancel, get payload, max payload length, and send. As you can imagine, we will use a lot the send command. Let's look a little bit at it, what it does. So you have to pass basically an address, which is the destination address of the message that you want to transmit. Then a pointer to a message T structure. This is the message that you want to transmit. And then the length of this message. And this function will basically enqueue this message for transmission into the operating system. So it will put these messages into a transmission queue. If this enqueuing is done with success, then this function will return success basically. So it's returning an error T, which is basically a Boolean variable, which can be either success or failure. Then once you have performed this sending operation, you wait for an event, as we have seen, and this event is called send done. Okay. So this event is signaled in response to an accepted send request. So whenever your message is transmitted by the operating system, the event send done will be fired, and you have to, again, write the code inside this function to manage this operation. At the same time, we may look at the receive component. So again, go here. Let's look at the receive interface. The receive interface is very simple and has only an event called receive, which will basically give us the message that we have received. Okay, so receive a packet buffer, returning a buffer for the signaling component to use for the next reception. So basically, when we use this interface, we have to be ready to intercept messages. So we will write code inside this event to handle the messages which are accepted. Again, we will look at an example now, so everything should be clear. So the example is the following. So we have an application that counts over a timer. So we have a timer, and each time the timer fires, we have a variable that is incremented. Okay, at the beginning is 0, after 1 second is 1, after 2 seconds it's 2, 3, 4, and so on and so forth. Okay. Each time this variable is incremented, we want to transmit a message in broadcast to all nodes which are listening, and we will put the value of the counter inside this packet. Okay, so we increment the counter and we transmit a message. Then we increment the counter another time and we transmit the message. The nodes who receive this message will get the message, read the value inside the timer, and use that value to trigger on the LEDs they have according to the number which is inside. So if the number is 0, all LEDs will be off. If the number is 1, only the first LED will be on. If the number is 2, in binary it would be 1 0 0 1 0, so only the second LED will be on. If the number is 3, which in binary is 1 0 0, only the third LED is on, and so on and so forth. Okay, so we will use these binary combinations in order to trigger on and off LEDs according to the number we read in the packet. This is an example which is called radio count to LEDs, and is again inside the application folder of TinyOS. So let's quickly look at the code and try to simulate it into Kuja so that we are done for today. So in order to look at the code, I will open it. So it's here in radio count to LEDs. Okay, and then let me open also this one. So let's look at first at the configuration. Okay, we have a couple of additional components now. Since we also want to perform send and receiving, we are using the sender component and the receiver component and the active message component for manipulating messages. And we also have main C for booting and LEDs for turning on the LEDs as before. And then we have our application, which is the radio counts to LED C. If we look at the implementation, which is here in the radio count to LED C file, we are including also a header file which contains basically the value of the timers. We have these three interfaces here: receive for receiving, AM send for transmitting, and packet for manipulating packet. And then we have the same interfaces that we have seen before, so LEDs, boot interface, timer interface, and so on and so forth. Let's see what happens in our implementation. So at the beginning, when this is the starting point of the application, as I have said, the boot event, first thing we do, we start the radio. Okay, so we turn on the radio. We will use these commands to turn on the radio. So this command is basically will turn on the radio and then will trigger an event, the start done event, to notify if the radio was turned on correctly or not. So if it's turned on correctly, so if this is a success, then we can start a timer. And in this case, it's a 250 milliseconds timer. Otherwise, we will try to turn on the radio again. Okay, this should never happen. So since we have started a periodic timer, we are expecting this timer to fire every 250 milliseconds. So what we have to do is to increment the counter variable, which was declared here at the beginning, and set to 0. So we will increment the counter variable, and then we will, don't look at this if so far, but we will basically define a message, this message here. We will set the value of this message to the counter variable that we have already incremented, and then we will call the send command to transmit this message in broadcast. Okay, so do you remember that this send command, the first parameter here is the address, destination address of the message. In this case, we are using the TinyOS constant broadcast address to specify that this message should be transmitted in broadcast. We pass also the packet, the size of the packet, and then we wait for this message to be transmitted. So since we have called the send, we should also wait for the send done event, which is here. So whenever the send done is triggered by the system, it means that that the message has been transmitted, so we can basically unlock our transmission. So we can put to false this variable, and note that this variable was the one that was checked here to see if we could transmit or not a message. So basically it's what is called a traffic light variable to see whether a message was already enqueued or not in the queue. So this block here will basically transmit our message, and this block here will basically receive our message. So whenever we receive a message, we have to read the content of the packet. So we will basically read the content of this variable and perform a bitwise AND operation to see which LEDs we should turn on or off. So these if statements here, for example, performs a bitwise operation between the counter and a bit mask with just 1 at the end in order to see whether the first LED should be turned on or off depending on the value of your counter. The same is done for the second and the third LED basically. So without looking at the details, let's try to compile this application. So we can do make TinyOS B here. Okay, the application was compiled. We can create a new simulation. Again, we can add a sky mode. In this case, instead of going into the blink application, we will go into the radio count to LEDs application. Build TinyOS B main.x. And we will create 2 nodes. Okay, so now I have 2 nodes here. When you have 2 nodes, it's good to look at the radio environment, which is basically something like this. So for each node, you have the coverage, so the transmission range of its messages, okay? So the green part, let's say, is the range in which messages can be received. The gray part is the range where messages can be received with some errors, okay? Outside of this circle, messages cannot be received. So if we move the 2 nodes, one inside the coverage range of the other, then we will have correct transmission between the two, while if the 2 nodes are outside of their transmission range, there will be no communication with the 2 nodes, okay? So if now they are outside their transmission range and I start the simulation, nothing will happen because messages will be transmitted but will not be received by any of these, okay? So you can see here we have some transmissions of messages, but we do not have any activities on the LEDs. The LEDs are basically empty, okay? So when I move one of the 2 nodes in the coverage of the other, then I start seeing that the LEDs are blinking, okay? So what's happening here is that messages are going from one node to the other. You see I have these arrows that shows radio traffic. Each message contains a value which is incremented each time, and that's why we see these LEDs blinking, okay? If I move them again, then they will stop blink. If I move them near to each other, the LEDs will be blinking, okay? So this shows basically a very simple example of radio communication with TinyOS and simulation, okay? And what I suggest is that you try to rerun these 2 examples, maybe look at the source code a little bit, try maybe to modify the values of the timer, okay, in order to understand what happens when you change these values. Try to modify a little bit, for example, the logic with which the counters are incremented, okay? so that you can start playing a little with TinyOS. Okay, next time we will stick again with TinyOS. We will see how to perform sensor readings. We will look at TOSIM simulator. We will see how to set up a network in TOSIM. And that's it, basically.